So the problem that you know already how to solve that we will be building on is a problem from scattering theory. So let me just run through here a quick review of the key aspects we will need from scattering theory. And then we're going to show you how this framework that you've already learned how to work within the wave mechanics formulation actually is mathematically equivalent to that kind of crazy Feynman sum over history. So here's the basic concept again, right? In scattering theory, we have some potential v of x, right, which is a function of x. And I'm going to have this divided into two main regions and in a scattering region. In region 1, the potential has some constant value. And in that region, I'll just be sending in an incoming set of particles, an incoming beam of particles, and it's going to then scatter off of the scatterer, and some of them will be reflected, generating a reflecting beam. Between locations x equals a and b, that's where I have all the unusual scattering type behavior occurring. And then finally, there'll be a region which I will call 2, where the potential again becomes constant. And then over here, there will be some outgoing beam of the transmitted particles. The particles will come in then with a given energy E. And corresponding to this, then in these regions 1 and 2, where the potential is constant, there are corresponding wave vectors, K1 and K2. Now you know already how to compute these reflection and transmission probabilities. The basic thing you do is that first you solve the time-independent Schrodinger equation for this system, and you do that after a lot of hard work of matching the various boundary conditions and solving the corresponding equations, and then you massage your results into the following form, where you may pull out some overall normalization factor, but you get things so that you have a unit incoming wave with wave vector k1, because this is in region 1. And to make the math easier, we always center things properly on the boundary where we will be matching the conditions. And then there's going to be added to this some amount of a reflected wave with some reflection amplitude that I'm going to call capital R naught. And again, this is now a minus sign because it's a backward traveling wave, and I center things appropriately at A. In region 2, you take the same solution and you identify then the pure state of momentum here on the right, which now has wave vector k2. It's written so that you are centered appropriately for the boundary point x equals b, and then whatever that prefactor is in front of there that you get, we call t naught. Finally, once you have this solution to get to the overall reflection and transmission probabilities, what you do is you look at the ratios at the magnitudes of the corresponding probability currents, right? The reflected probability is the fraction of particles reflected, which will equal the total number of particles per unit time that are reflected divided by the total number of particles per unit time that are sent in. That gives you the fraction then that are reflected and the reflection probability. You do likewise to determine the transmission probability. And the last key ingredient then is how we calculate these probability currents. And as we've learned, the way you do that when I have a wave like so, with some generic prefactor C naught, with a wave vector K, which could be either going in the plus or minus direction, where I've written this as centered at some arbitrary point, which I will call C, right? The final probability current then is the probability density of this wave, which is just the magnitude of C naught squared, right? Then times the magnitude of the classical velocity. So this actually would give me then the current density C. I'm only interested in its magnitude. And so it would be its density squared times then the corresponding classical velocity. So that's how we normally calculate things. To show that these final outcome probabilities are equivalent to the Feynman formulation that we've given up above here, right? We're going to do this in 3 stages. First, I'm going to introduce a new normalization convention. So I'm going to introduce a new normalization. And along with this, I'm going to introduce a new notation. And doing that then is going to align things up very nicely so that, in fact, I can calculate probabilities just as the magnitudes of corresponding quantum amplitudes. Next, we are going to think about, well, what actually constitutes events and histories in this case? And then finally, I will show you that the result we get from solving the wave equation is, in fact, exactly expressible in terms of this type of sum over histories and product over events. So let's begin then by adjusting our normalization and our notation. The key thing that I want to do is just kind of a minor thing, is I want to change our perspective on what we consider a unit incoming wave. I want to take this wave that's coming in that has a particular amplitude on it, which I'm calling C0, and I want to rewrite it where I think of my pure momentum states as having a different normalization. I want to rewrite it as e to the plus or minus I kc. X minus c will be my pure state, but then to normalize it, I want to divide by the square root of the classical velocity, h bar kc divided by m. When I do this, I will have exactly the same type of a wave represented, but now, of course, I'm going to need a slightly different prefactor, capital C. And you can see quickly how to convert these. The new c is just the old c times the square root of this classical velocity. Now, the reason why I would do such a thing and introduce a new normalization convention is that now there's a much simpler formula for calculating the current densities and ultimately the probabilities. Because the current density now, it follows exactly the same math as before. It's modulo C0 squared. But C0, notice, is really C divided by the square root of the classical velocity. So that's h bar kc over m in my square root. This has to become squared, and then I multiply by the classical velocity, which is h bar kc over m. So now I hope you can see the convenience involved in using this type of factor as my unit incoming wave, because notice when I calculate the probability currents, when this comes out of the square, when I square this in the denominator, it will exactly cancel the numerator portion. So my current densities are just, if I always keep these appropriate normalization factors on my momentum states, become then just the modulo squared of the corresponding amplitudes. Now, once we have this, then, we can think about what our solution should look like if we rewrote it not in terms of these as our unit waves, but in terms of our new unit waves with our new normalization. So I'm going to rewrite my original solution then in the following way as a phi 1 of x then is going to equal some unit amount of an incoming wave, e to the I k1 x minus a as we had before, but now it's going to be normalized by, with a slightly different norm, h bar k1 over m. And then there is, of course, always the reflected piece, which I will now call r, because it often will have some adjustment factor necessary, multiplying an e to the minus I k1 x minus a divided by its square root, h bar k1 over m, like so. And then I will have phi 2, which I will write again as a new factor, capital T, not a T naught, times then corresponding transmitted wave k2x minus b divided by the square root of h bar k2 divided by m, like so. So my job then would be to rewrite a solution that I had previously had, right, into this new form. Now, one way, of course, you could find this r and this t would be simply to assume these forms, right, and then use them to match your boundary conditions, and then you could actually get equations to solve for r and t. Another way is we can just quickly do it by rearranging the original equation that we had up here. Right? This is my one particular bound state. How we normalize these states ultimately, of course, is up to us. We had arranged for this to be a 1 in front when we did our scattering problems by simply pulling out whatever prefactors were on this first term and gathering them into the shape of our waveform when we did our quantum superposition. So since we can pick our norm at will, I want to pick the norm for this overall wave function that aligns then with my new normalization convention. So it looks like if I want 1 times this wave divided by this factor, I should simply take my original wave function and divide through by that factor. So I would be dividing through by square root of h bar k1 over m, which would divide the second term through by exactly the same factor, h bar k1 over m. And finally, that would divide through, I have to divide through my entire wave function to pull out this overall normalization. This is then going to be divided by square root of h bar. K1 is what I should write in here over m. I should put a K1 in here, but notice the normalization convention that I have wants me really to put a K2 down there. So the way I can handle this is just by adjusting some of my additional prefactors. Right? If I really wanted to put a K2 down in there, I can maintain my equality by putting a K2 in that denominator as long as I put a K2 square root in the numerator. But of course, don't forget what I was dividing through by had a square root of K1. I can't forget the K1 that had to be in there for my overall normalization. So this wave function as I've written it now is exactly equivalent, up to a normalization constant, to the wave function now in my favorite form. Finally then, by comparing these two, I see how to translate my new normalization, my new amplitudes under my new normalization convention to my previous amplitudes. In particular, you can see that the r's actually align perfectly. So in fact, r will equal the old r naught. But the new t that multiplies this waveform with the K2 in the denominator has a slight adjustment with that K2 in the denominator. It's a T naught times this square root factor. So that will equal T naught times the square root of the K2 that had to go on top divided by the K1, like so. Now, that's how we can get to this form. The advantage of this form, though, and in fact, when I write the form this way, I really wanted to leave a little bit of space down below it. So, because I want to introduce a new notation. So let's just move this down here a little bit. The reason, the motivation for finding these new coefficients is that now the probabilities are more straightforward to compute. The reflection probability, for example, which is the reflection probability current over the incoming probability current. Now, this reflected probability current, because I have this new normalization here, that current density is just the magnitude of r squared. The incoming wave has a prefactor of 1 with our new normalization, so its probability density current is just 1 squared. So the final result is that to get the probability of reflection, it really is just the square of a quantum amplitude, just like the Feynman framework says I should be able to arrange. Similarly, the transmitted component will be the transmitted current over the incoming current. The transmitted current is also written with my more convenient normalization convention, so that will be T squared on top. The incoming current, again, is just the modulo of 1 squared, so this will equal the modulo of T squared. So, by using now this new normalization convention for what we mean by a pure momentum state, we've aligned things properly so that my reflection and transmission probabilities are nothing other than the squares of the corresponding amplitudes. And our job then turns out to be, just as in the Feynman framework, right? We now have exactly the same formula for the probabilities. Our job is to determine how to calculate these amplitudes, how to calculate the R and T. The first step along those lines is to help us organize our math here is to introduce a little bit of notation, just to make our lives easier. This, as you can see, with this normalization convention, gets to be quite a mouthful to write down. So I want to introduce a new notation, a shorthand for representing just this type of function. And I will write a new symbol for it. This function represents a wave traveling to the right. So I'm going to actually represent it by a new symbol, which will simply be a wavy line with an arrow that tells me it's a wave moving to the right with a plus sign. To finish writing down the formula, the key ingredients I need to know are where this is centered and what the value of k is. And I can get both of those into my new symbol by including a vertical dashed line and just labeling the x value at that point A. As soon as I do that, when I have a line like this touching my arrow, that by convention I mean that the arrow is the corresponding complex exponential centered at the labeled location. The last thing I need to know is, well, what value of k should I use? But that also is clear from context, because by drawing it this way, we can see that this wave exists to the left of x equals a, and all the points to the left of x equals a just have wave vector k1. So that is how I would denote this first term. I can go further, though. If I want to represent the fact that this now just represents what's in these parentheses, if I want to multiply it by a factor, I can use the same notation we use in any kind of algebra. No matter what my factor is, when I multiply it by a number, I just write the number in front of it. So I could represent even the factor of 1 by just putting the number in front of this wave, meaning take the number 1 and multiply by this symbol, which denotes exactly this term. Similarly, when I go to the reflected component, I can write a symbol that would represent this. Now I would want a wavy line that's pointing backwards. I'm still centered at location x equals a, and I still have the same wave vector k1, so I could actually represent this term as a backward traveling wave. And because, again, of its location, I know it's wave vector k1. It's touching A. That gives me my centering. The backward arrow tells me it's a minus sign. And finally, to represent the factor in front, I would multiply by r. And the last thing I would need then to represent this entire term, which is what this diagram now is representing, is a new convention which simply says if I have a picture like this and I have two arrows in there which represent forward and backward waves, of course I mean that the wave function itself is just the sum of these two. So this sum is just implied by the fact that I see both of them here on the same side. The last bit then is I need a symbol to complete my entire wave function, which of course is defined in these two different regions. So to represent this transmitted piece, I would have a vertical dashed line. I will label it B because that's the location of that boundary. And I will denote this term as follows. And notice my convention now still works. Because the line is touching the dashed B, I know where to center it. I have the prefactor T in front. And finally, to know which value of k I should use, because I've drawn this to the right of B, I know I should be using a k2 by my convention because all points to the right of B actually have wave vector k2. And by combining both of these, then I have a single picture that represents my entire scattering wave function. I haven't spoken much about, of course, what's going on in between here. You know, we could put a couple question marks there if you like, because we're not really concerned about that part of our wave function, but the entire point is this cute little diagram is a quick way I can represent all of this mathematics. And this is what's known as a Feynman diagram. It's nothing other than a quick way of representing a more complicated mathematical expression that you just don't feel like writing down. Right? It's nothing super mysterious, right? That's the beauty of these Feynman ideas. It's just a very convenient shorthand that we will see is very powerful in helping us organize our mathematical thoughts. And whenever one looks at a new problem, one generally has to come up with a new set of conventions to represent the underlying mathematics, so you always end up inventing your own new Feynman diagrams for each new type of problem that you would solve.